Hi. So today's recitation is about model explainability and interpretability. And this is the second last recitation. So what we'll cover today is a lot about explainability and interpretability of a model. I'll talk about how they're used interchangeably and maybe and even a demo at the end. So explainability is the process of being able to explain what the model predicted and why it predicted this. And to explain the model, first we have to interpret it. And both of these terms, interpretability and explainability, are used interchangeably, but there's a very slight difference. So let's look at interpretability. So I think before we look at interpretability though, explainability is you explaining why the model predicted what it predicted. Whereas like when you talk about interpretability, it's the degree to which you can understand what caused the model to predict what it did. So you trying to understand that, okay, like a decision tree was able to give me this yes or no output was because of these factors. Whereas when you explain it to someone else, let's say you are doing credit scoring and you want to explain to your customers that why we took a decision like this, that's where you want to explain it to them. And that's why these both go hand in hand. There's a second definition too of interpretability, which is the degree to which humans can consistently predict the model's result. So let's say you look at data like the German credit scoring data, and you look at someone's profile. You can see the duration of their credit line. You can see maybe which age category they fit in. And maybe by looking at that result, you can kind of predict, are they high risk or low risk? And using that, like you can kind of interpret what the model would do. And if you can consistently do that, you can pretty much interpret what the model will do. A lot of the material in today's recitation is also from this book that's linked here and at the references about interpretable machine learning. So why is this important, right? So to make models better, you need to really understand the model. You need to explain the reasoning behind the model. So to be able to understand it, you need explainability. And in certain cases, if you're not a researcher and you're just not trying to make the models better, if you're in the industry of certain regulated industries like finance or healthcare, in those cases also, it might be really required, and it might be required by law that you give your decisions. So in my case, I interned at this life insurance firm, Munich Re, over the summer. And there we couldn't use a lot of deep learning models because they're not very explainable. Whereas we could use some of the models like random forest, decision tree, XGBoost, which work really, really well and are explainable too. And of course, when you want to ensure your models are fair. So last week we had a recitation on bias and fairness. So if you're not able to explain what the model is doing, it could also be that the model is biased and it might be unfairly judging certain demographics of people. So as we know, like the model learns from our data, and because humans are inherently have been at least biased in the past, maybe even today, the model might learn bad things. So we want to be sure that the model is not doing anything nefarious. Now let's talk about some interpretable models. So these are some common 5 ML algorithms you might have seen. And all of these, when you actually think about it, are very intuitive, right? If you think of decision trees, it's just if and else, right? At multiple levels. Like if you look at this, this graph, like of a shooting game, this decision tree of a shooting game, it tells you like what action should you take. So if you see an enemy, you ask yourself, do you have ammunition? If you have, then you engage with the enemy. So things like that is just an if else. Knife base is a counting algorithm. Linear regression, you're seeing distance from the line. Logistic regression, you're just seeing, you're classifying a data point based on which side of the line it is at. And k nearest neighbors is again a measure of distance from certain points. So yeah, these are very intuitive and these are explainable. But then there are certain networks, like especially deep neural networks and deep learning methods. They are very complex and convoluted. So yeah, pun intended, because CNNs. So yeah, let's talk about deep learning networks, because these are really important, right? They give us great performance and they work really well. But the thing is, because they have millions of weights and biases, they interact in such complex ways that it's not easy to interpret them. So this is an image of what a CNN does to a human face. It puts it in a very high dimensional space and has a latent representation of it. So here we're able to plot it using TSNE, which is just an algorithm to plot something in 2D, which is actually in a very high dimensional space. So although in this case, it looks distinct, but it's in a extremely high dimensional space of like 20, 30, 40 features, whatever you want to give it. And it's just not intuitive. You can't just understand deep learning models. So that's why in certain cases, when you want explainable models, you do not go this route. However, there are still ways, and we can talk about it. So yeah, let's talk about how do we actually interpret the model. So there are two ways. One, you can interpret the whole model. You can see how important a particular feature is to do a prediction, or how important one particular feature is given the output. So there are two popular methods for this. So first is partial dependence plot. So this is the image on the left. It shows the relation between one feature and the outcome. So let's say in this case, if someone is male or not, and how the risk is calculated using the credit scoring data. So in this case, as you see, as the variable changes, so it's actually just between 0 and 1, you see the risk also changes. This is, of course, not a good thing because someone's gender is a protected variable and it should not be factored into their risk. But in this case, I trained the model on it. So anyway, it learned this. The point is that with partial dependence plot, you want to see how the model reacts given how a feature changes. The second way that you interpret the model is feature importance. So in sklearn, you have an inbuilt coef function. We'll see both of these in the demo too, and you'll get to work with it. Using feature importance, you can actually rank the features. You can see by magnitude which feature is contributing most to the output, and depending on the sign, where it's swaying the output. So in case of a decision tree, the magnitude just tells you, like in this case, that the credit amount, which is the feature on the left with the highest magnitude, its value is contributing most to the output of someone being high risk or low risk. Whereas something like a logistic regression, since it's classifying into two classes of high and low risk, there can be a sign attached to this too. So it could be like between, like, it could be positive or negative value. But again, the magnitude really tells you. If the magnitude is close to 0, the feature is not even factored in. But if it's the higher it is, the more important that feature's value is to the model. Now let's talk about a single prediction. So earlier here, these two methods, they work very well on the model as a whole once you've trained the model. But in certain cases, you want to interpret a single feature. So let's say someone applied for a credit card with you and you want to give them a decision. You might reject them. And in that case, you need to legally provide them with the reason. So in that case, you need to be able to interpret and justify a single prediction. So in these cases, these two methods come in really well. So one is SHAP. It stands for Shapley Additive Explanations. It's a game theory based methods, and it calculates the contribution of each feature for a certain prediction. So we'll see this in the demo too. Like there's a whole visualization for it. I'll show you in the demo. I think, yeah. Anyway, so with SHAP values, you can actually see like how much someone contributed to the end result. The second method is counterfactual. So it's like almost like a null hypothesis situation. So you see a causal relationship between the output and the inputs. Like, let's say, like if the output is you burning your tongue, and the input is the temperature of the coffee you drink it at. So a statement like, if you hadn't sipped that hot coffee, like the feature value of hot coffee, if it's 0, then the output value of you burning your tongue will also be 0. Like you don't burn your tongue. So something like that. So with counterfactual, what you do is you try different permutations of the inputs to see which one of them flipping would actually change your output. So again, we'll see this in the demo, and it's actually demo time. I think we can go over the code then. So yeah, first you're just importing stuff like these two libraries. They're not installed by default. So SHAP is, as we discussed, for explaining a single point. And you import a bunch of models from like sklearn. So we'll train a bunch of these models and we'll see what works. So of course you load the German data set, the German credit data set, you clean it so that all of your data is now one hot encoded. You split it. So a lot of this we did last week in the fairness recitation too. But yeah, I think you don't need to care about that. Like that's happening. But yeah, let's come to this point where you have 4 classifiers. So you have this dictionary of 4 classifiers. And so when you run it, you should get somewhat comparable validation accuracies. So yeah, so these are like sklearn models out of the box. So you're just giving it, you're just training it on X-train, Y-train. You are calculating the accuracy score for them, and you're just storing these metrics. So whatever the trained models were are still stored in classifiers. So as we see, like, our neural network didn't perform too well, which is okay because neural networks typically require a lot more data points. In our German credit data, we only have 1,000 data points. So something simpler like logistic regression, decision trees, or XGBoost would also suffice. Let's try working with the decision tree here. So first, since we spoke about partial dependency plot, right? So with partial dependency plot, you want to see what happens to the output when you vary the feature value. So that's why your feature value here is on the x-axis. So let's say for the job value, if you vary that within certain bounds, you see how much the risk changes. So it can go higher or lower depending on the encoded value. So in this case, our job category was encoded in these 4 points. I think then similarly with depending on someone's gender, it was also varying. With PDP, you can also do something interesting is that you can put 2 features together. So if you look at the third plot, which basically maps job and gender, you can see how different the outputs would be. So it's creating these regions of color, which kind of determine the boundaries of how the risk changes given these 2 variables points changing too. So
when they say like 1.0 and like 2, like what does it mean by that job?
Where in the colored one?
Just the axis job, like what is 1.5?
Sure. So in this case, because you're passing it through to a model, you have encoded all of these values. So by default, the data set, it would be something like this. It would be encoded in certain value, like 1, 2, 3 or 0, 1, 2, 3. So it would be subcategory if you look at the data dictionary. But I think maybe we don't have to worry about that. The point is it's just something different.
I thought it was like 2 jobs or 3 jobs. Okay.
Yeah, I mean, it could be that. It could be that. Like I don't recall the data dictionary there, but it could be that maybe this person is doing 2 jobs. So no, yeah, I think that's a valid explanation. So maybe it's like score someone lower if they have 2 jobs, because like they're maybe not financially that well. But if someone has 3, maybe they're doing better. I don't know. And yeah, so a lot of this could happen that, let's say you're looking at, so someone comes back to you saying that, my credit card application was rejected. What can I do to improve? So if you have like a multivariate graph like this, the colored one, you can see, okay, what values do they need for their features to actually qualify for a lower risk? So you can kind of suggest that, okay, you need a lower value of your maybe number of credit lines or things like that. And you can suggest them these things. The next thing I want to show you is feature importance. So once you train a model, you want to also see how much a certain feature is important for the model to actually make the prediction. So you do that in sklearn using, so it depends on model to model, but let's say for logistic regression, you can do this coef, and you can see the data. So I take the 0th element because it was anyway a list with only 1 element, and 20, it was a size 1, 23. So I just took the 0 to take it out. I sorted the dictionary and this is what I get. So I see like the purpose for education ranks the highest in this case. And then the other factors come in. So you can plot the same thing here too. So using this plotly graph, you can plot how certain things are affecting the score. So as we discussed, the higher the magnitude, the length of the bar, the more it's actually contributing to the output. And this is for overall the whole model. So not an individual prediction, but overall, like the biggest bar here is the purpose of like domestic appliances. So if that is there, like, depending on its value, it can really sway the output. Because it's negative in this case for logistic regression, what it means is that it's swaying the value towards 0. So I think in this case, 0 meant low risk, whereas 1 meant high risk. So because of that, like if this value is really high, this feature is contributing to telling us that it'll be a low risk person. Similarly, I've done it for decision tree too. And as you'll see, different models learn different features differently. For the decision tree, the most important factors are credit amount and duration, which were very different from what our logistic regression learned. So, these are features. This is also something good to know. So how do you explain it in your model? All right, so I think we can go to the third part, which are the SHAP values. So when you're working with Shapley, it works on a single prediction. So what you do for this is that you are explaining a single value, and for this, you can see this graph is generating. So you are telling it like for the expected value of index 1, which means like the output being 0, you are seeing what features actually contributed to it the most. So in this case, for this person 0 in the data, the duration contributed the highest. Then the next highest was the age category of being young. So for them to be low risk. Similarly, you can plot someone's data for being high risk. In this case, you see what contributed the most for that particular individual was that checking some checking number or something like that's one of the features that really affected them there. I think actually in this case, because between 0 and 1, the sum of it, the higher, the more it is, the more it's pushing someone to 0. Whereas if the sum of the red bar is higher, it's pushing them to 1. Then there's also a summary plot. So although SHAP is usually for one particular output or one particular inference, you can also have a summary plot, like how much did one feature contribute overall to all the data. The fourth thing I want to show you is counterfactuals. So as we discussed, counterfactuals try to make different permutations to see if they flip certain features, how would that affect the output? Use the dice library for that. And let's see the first output. So it tells you that the original outcome was 0, which is low risk. And it tells you, gives you the data frame with the whole data. What it says now is that it created, because we told it create 2 number of counterfactuals, like that was an argument to the function, that total CS is equal to 2. You're telling it that generate me 2 counterfactuals, generate me 2 examples that would flip the model's output to 1. So it gave us 2 of these answers that, okay, what would be different? And you can compare these 2 inputs and outputs to see what did the model do differently what did the model get differently this time that actually made it flip. So in this way, you can kind of see that, okay, if one thing was different about that person, how would that change the model's output? And similarly, like again, I tested for another case and you can see the answer. Thanks for coming. A lot of the references are here. A lot of the material in this presentation was inspired by this book, which will be linked here in case you're ever interested now or in the future. To use SHAP plots, there's a whole tutorial also that I used. So you can go to that. It's a Medium article. So there's more data on SHAP if you want to know. I would really recommend. The book was cool and very succinct. So yeah, thanks for coming.